Hi everyone, I'm Mike Erbach, and today I'm going to present our work on creating domain-specific accelerators from PyTorch programs with MLIR and CIRCT. I'm going to quickly introduce MLIR and CIRCT and explain why we think it's a great fit for HLS. To show some of the flows we support and the abstractions we use, I'll demonstrate our compiler stack with the CIRCT HLS tool. After that, I'll mention some future work and why we hope this can be useful to our community. So very briefly, MLIR is a compiler infrastructure that grew out of the need for better tooling for compiling machine learning programs. It needed to be more general than LLVMIR, and the same needs that make MLIR good for machine learning make it good for other esoteric domains, like hardware description. That's where CIRCT comes in. It's hoping to do for EDA tools what LLVM did for software compilers. CIRCT is built with MLIR to provide common abstractions for hardware description in a first-class way, just like MLIR does for machine learning. By combining them, we have all the ingredients we need to do HLS using a common infrastructure. By transforming programs from low-level MLIR dialects to high-level CIRCT dialects, we can connect the dots. The different flows we support and the dialects they use are depicted in this diagram. The dynamically scheduled flow can excel in situations where memory dependencies must be resolved at runtime. The statically scheduled flows create finite state machines, enabling FSM optimizations. When memory dependencies can be analyzed at compile time, the static flow can automatically pipeline loops and further optimize the FSM. At every step of the way, we're able to pick and choose the right level of abstraction to capture the information we care about. This allows us to focus on the particular HLS techniques we're employing and opens the door for compiler extensions at each step. Now I'm going to walk through the different flows and the IRs they use. The CIRCT HLS project contains a command line tool to drive the compiler stack. To start off, let's look at the machine learning program we're going to compile as input. This is a PyTorch program, and for now we're just going to look at a matrix multiply. We'd love to support entire neural networks and things like that. And I think we're getting very close to that point. But for now, we're going to focus on a mapmul because it helps us look at the different pieces of the stack with a program we can actually understand. So when we run our stack, we have different ways that we can run our command line driver. This is called HLS tool, and we basically specify which flow we want to use, what file to compile, what's the shape of the inputs, and things like that. When we run the tool, it's going to run a bunch of different compiler passes, and before and after each pass, it's going to print out the IR at every step. That's super helpful for debugging, or if you just want to pack on something and plug in at a certain stage, you can grab the IR at a certain point in the lowering and use it. In addition to lowering all the way to System Verilog, it's also allowing us to build a test bench that can be expressed in a high-level language. We also are looking into doing co-simulation in higher-level languages, and generally tying into the verification process from the higher level. Finally, after building the simulator, it actually runs the test bench with Verilator, checks for the correct output, and produces a BCD trace. So these are all things that you can do on the command line with HLS tool. To understand how we actually lowered that program, let's take a look at what the Torch MLIR produced. So here we get a program at the level of linalg on tensors, which is a really interesting level of abstraction. We don't have time to talk about what you can do here, so we're just going to focus on how you can lower it. But there's a lot of really interesting work going on at this level of abstraction. So to bring this program closer to hardware, we lower to what is traditionally considered the code generation set of dialects in MLIR. Except in our case, we're generating hardware. So this is the control flow dialect, which has things like branches and basic blocks, and basically represents a control data flow graph. So it's a lot like LLVMIR, and this is what we use when we're doing dynamic scheduling. So on the dynamic flow, we lower that to the handshake dialect. The handshake dialect takes that control flow and realizes it into the data flow in a graph. So for example, in the blocks, we lower those to muxes, which now have as inputs both data and control signals. And so the control data flow graph gets made explicit in terms of what are the signals going in and out. And then we have a way to lower each operation in the handshake dialect to latency insensitive hardware. So this data flow graph with control and data flowing through it gets lowered into hardware that is latency insensitive and realizes the overall computation. So that's our dynamically scheduled flow. And if we pull up the hardware, what it looks like is a bunch of handshake modules all being instantiated in the top module. And now each of these components has their own valid and ready signals to implement the handshaking and data signals to actually let the data flow. Something else that we can do on the dynamically scheduled flow that's super interesting is tie a visualization to that low-level hardware. So we have this tool called the Handshake Debugger that Morten built, and this lets you visualize the handshake data flow graph. Data edges are dark and control edges are dotted, and it lets you step through that VCD trace. So when the lines are red, that means no tokens are flowing. When the lines are green, they flow. When a line is yellow, there's something blocking it. So you can see I'm stepping through in the console, and that's actually allowing the visualization to represent what's happening at the hardware level. So you can see these mucks, for example, went from orange to green on step 23, and that can help us debug issues, and it can help us understand our dynamically scheduled circuits. So that's super interesting. One of the many things that working with MLIR enables, because we have this handshake dialect, we can tie the handshake dialect representation to the hardware representation. Okay, so moving on to the statically scheduled flows, these flows are going to create finite state machines. That's what we mean by statically scheduled. In the static flow, we use the calyx dialect, which can represent a finite state machine and a data path. And from the MLIR side, we start at a higher level, and that enables us to easily build this finite state machine. So we start at the level of MLIR structured control flow dialect, SCF. Instead of basic blocks and branches, we have while loops, which make their condition explicit and pass loop carry dependencies in an explicit way. We can lower that to the calyx dialect, which enables us to capture that same while loop structure in the calyx control language. So that we used a little more high-level information by starting from the structured control flow, and that brought us to the calyx dialect more directly. Here, when we generate hardware, I want to note that we're generating latency insensitive hardware by default. That's what the calyx compiler does. So we have in our finite state machine transitions, we have this combinational logic that's gating the transitions. We can capture even more high-level information and improve on that. That's by using our static flow with the pipeline flag. So if we enable the pipeline flow, this is going to cause us to run an analysis at the affine dialect level in MLIR. When we do that, we're able to schedule the program using circuit scheduling infrastructure, which is the subject of a whole nother talk at this workshop. Suffice it to say, the schedule produces an optimal pipeline, which we can then realize in hardware. So the way we do this is starting from this affine dialect, which makes the looping explicit. When we are able to analyze the dependencies of the affine loops, we're able to generate what's called a static logic pipeline. So this captures the data flow through the pipeline explicitly in SSA values, and then it makes a control flow of the pipeline explicit via attributes. This gets lowered to calyx and enables the calyx compiler to optimize the circuit and produce better hardware. So we still have that while structure, and the body is now enabling an entire pipeline in parallel. If we look at the generated Verilog, we can take a look at the finite state machine and see that now it just transitions directly on the correct cycle. There's no more latency and sensitivity. So we used more high-level information, and that helped us generate better hardware. So stepping back to the slides, we have a whole bunch of really interesting projects that we can work on now, and we're really excited for other projects to start trying to integrate at the level that makes sense for them. Taking a step back, where are we today? We've taken a few different paths that have been studied before and implemented them using MLIR compatible tooling. Now that we've worked out how the different layers can compose, we have a scalable compiler stack for HLS that lets you plug in your innovations at the right level. All the abstractions above and below you are taken care of by other pieces. We're hoping this can lead to really positive network effects, where improvements at one layer can improve many end-to-end flows. Hopefully you found this interesting, and if you work at any of these levels, we hope you'll consider connecting your work to CIRCT. If you want to get involved, check out the website, GitHub, forums, or Discord. And finally, we want to thank everyone who's been involved in these efforts and the LATTE organizers for putting together this great workshop.